Alright, grade 12s. So what I just explained in that brief video showing you the virtual ripple tank is I showed you that when waves pass through a double slit, okay, so two openings, they behave like 2 point sources. And so sometimes we call the kind of interference, so nothing really new today, it's just showing that it works in another circumstance, two source interference, sometimes we call it double slit interference. You get, I keep doing that, interference. Okay, you get the same pattern, okay? Because of diffraction, you get the same pattern. So all of these equations apply, okay, to whether it's double slit or whether it's two sources of waves, okay, that are vibrating in phase. Regardless, both circumstances, you get the same set of equations. Now there is one more there's one more equation that goes with this that I want to explain what it is. Let's say I had another nodal line here on this one, Pn plus 1, and the distance here I'm going to call delta x. That's the spacing of the nodes, okay? So like there'll be another node over here, there's another delta x here. What you'll find is they're all about the same distance apart, okay, for double slit interference. And what you'll find then is here, regardless of whether it's nodes or antinodes with double slit interference, the spacing will equal L lambda over D. There's a way to derive this formula. I'm not going to bore you with the details like I did yesterday. I wanted to show you where the basic equations came from yesterday because you're going to need all these equations. But for this one here, I'm just going to add it to the list. This is delta x equals the spacing of the nodal lines or antinodal lines. What I'm trying to do is we're going to build up to a little experiment I'm going to do later this week with a laser beam. And I'm going to show you that this works. I'm going to show you that you get this kind of interference when you shine the laser through two slits. And we're going to do more than that. We're going to measure the wavelength. Okay, like I'll show you how you would do an experiment like this to measure the wavelength, okay, of the laser. Alternatively, if you know the wavelength of the light you're using, okay, you can use this experiment to measure a very small distance, okay? Because D, the spacing between the two slits, it could be like the width of a hair apart, like just this tiny, like a micron apart. And you couldn't measure that with the naked eye or anything like that, but you could measure it with diffraction, not even using a microscope. In fact, that's how we measure distances between atoms. We do it using X-ray diffraction, okay? And this diffraction experiment, when you use two slits, that's called light diffraction, right? And that produces interference. Using that interference pattern, we can actually measure really small distances. So like distances like the letter D here, which is the distances between the centers of the two slits. So I'll just say it here, D equals distance between sources. Or in the case of double slit interference, centers, the centers of the two slits. So what I mean by that is if you have a wall like this, and here's another wall, okay, this is sort of a top view, and here you have a third wall over here, okay. These are your two openings that we call slits, okay, and D would be this distance here, the distance between the slits. You know, you would get your interference pattern radiating here. I'll use a different color. I'll use my, you get your nodes and antinodes sort of radiating outwards like this, okay? Same picture as you see above, okay? Just like this. So you'd have your two slits, here's a wall, here's a separating wall, and here is another wall over here, okay? So you see, here's your two openings. So just imagine it like this. Here's your two openings here, okay? And this pattern, the two holes act like two sources, and so you get the same pattern. Okay, so that's the deal. And we developed a new equation today. Not developed it, but I showed that there is a new equation. That one I put in the box. Very important for the laser experiment. That's the only one we use. Okay. Now before I leave you today, I didn't really have anything new today. I'm going to explain what double slit interference was. I wanted to do that, and that we use all the same equations. So there's really nothing new. It's still two-source interference, except now we see that it works with double slits also. Okay, now I wanted to leave you with some questions here that I pulled on this topic, okay, from your homework. Not from a homework, from a test and stuff, but I think there are similar questions in the homework. So if you look at this, these are all based on two-source interference. Okay, so let's read this question together. It says, in a page in a student notebook lists the following information. N equals 3, so that is the node number. Okay, that's nodes. We use M for antinodes, right? M as in Michael. Xn is 35 centimeters. Okay, L is that variable from the slit centers to the node, 77 centimeters. Whoops. D is the separation of the two slits or the two sources, so it's 6 centimeters between them. Theta n equals 25 degrees. And then it says this weird piece of information here, 5 crests equals 4.2 centimeters. Now, if you look at question, okay, that's important for one of the questions here. It says calculate the wavelength using 3 methods. Well, first, because they tell me like somebody measured the waves directly, I'm going to use this number. So if I have 1, 2, 3, 4, 5 crests, and across those 5 crests is 4.2 centimeters, okay? Well then, what I can do is I can measure the wavelength just by saying, all right, I've got 5 crests here, but how many wavelengths is that? Well, from here to here is 1, so that's 1 wavelength. 2, from here to here, 3, and 4. So even though there's 5 crests, because a crest is a half of a wavelength, that works out, like I have crests and troughs in between, but it works out to actually 1, 2, 3, 4. So 5 crests with troughs in between equals 4 wavelengths. So I would go like this. 4 wavelengths equals 4.2 centimeters, right? Just solve it for wavelength. So wavelength would be, I'll just use my calculator, 4.2 divided by 4 equals 1.05 centimeters. So I got 1.05 centimeters. Okay, so that's one way to find the wavelength. Now it says use 3 different methods. 3 methods. So that takes care of one. Number two, we're going to use some of our other formula. Okay, now because they give us all these variables, I know that one of the formula I can use is xn over L equals n minus 1/2 times lambda over d. That's one of our formula on the list, right? Now I'm going to solve this for the one that I don't know, which is the wavelength. Okay, now I'm not going to use the answer from number 1 to get the wavelength. That's one method of finding it. Well, this is another one. Okay, so I'm just going to plug these numbers in. N is 3, right? Xn is 35, okay, and so on. So it's 35 over here. We have 35 over 77, right? Okay, so let me just plug all the numbers in. Okay, so just excuse me a moment while I do that. And then times 6. I'm going to leave everything in centimeters. I get 1.09. Now I notice right away that these two values, that one and that one, aren't exactly the same. That's okay. Okay? There are sources of error. This is actually supposed to be data from someone's experiment. Okay, number 3. The other thing I can use is sine of theta n. So sine of theta n is equal to n minus 1/2 times lambda over d, right? So I can just go ahead, since I know that theta n is 25 degrees, I'll just go ahead then and solve that for wavelength. So, and I'll plug in all the other values, right? So I go 25 sine divided by and times 6 and I get 1.01. All right, so now I'm going to underline that with a rainbow. Now I notice I got 3 different numbers. Okay, so these 3 different numbers all represent the wavelength, right? So which one's right? Well, the most accurate one, this should be your reference because you measured the wave. You measured the wave directly. So that's your reference value. It should be the best number. Okay, you actually measured straight the waves. You measured the wavelength, 5 crests, and you got, 4.2 centimeters. So that's how that should be a direct measurement of the wavelength, should be the most accurate. These other 2 are based on our approximation, but we see that they're not bad. Okay, like the first one is within 4%, and the second one is also within 4%. Okay, so basically we're within 4% of our value, and often our measurement error is greater than 4% anyway, or it's around like 4 to 5%. And so that's acceptable error. Now when we do it with the laser, our measurement error will be actually way less than that, even with the approximation. So I'm just going to tell you, like, these 2 are based on approximation, but they're good approximation. Okay? Some students will say, why do we bother with the approximation? Well, here's the deal, okay? The reason why we're doing this, the reason why we use these other weird equations instead of just measuring the waves directly is because with light, we can't see the waves. And so you can't do it using method 1. You must use method 2 or 3, okay? And it's really the only way to do it, okay? So we don't have a choice with light. We can't see the waves. We don't see crests and troughs directly. They just don't look like crests and troughs with light. They just look like, what light looks like when it enters your eye. And right now I'm looking at light all around my bedroom. I don't see any crests or troughs in it. That's because that's not how I perceive light. It's the same thing with sound. Sound has compressions and rarefactions in it. You don't perceive it that way. It's just a sound. Like when a compression hits your ear, it makes a sound. When a rarefaction hits your ear, it makes a sound. And those 2 things will sound the same, actually. Okay, a push or a pull will still stimulate based on its frequency, and it doesn't matter whether it's a push or a pull. Same thing with light. Like, it doesn't matter if it's a crest or a trough. Your eye sees the same thing. So there's no way to distinguish crests and troughs with light, with your eye, and therefore we must use these other equations. That's why we developed them, okay, for that reason. And these approximations are excellent for light. Okay, because the sources are so close together and the point on the node is so far away by comparison, it's a really good approximation. It works very well. Okay, so now I already explained this one. It's because of the approximation thing. That's why they don't produce the exact same value. Plus there's measurement error. I'm just going to say, and measurement error. Okay? All right, so now in the diagram to the right, 2 sources are in phase at the same frequency. And this is a multiple choice question, as you can see. It says the wavelength of the waves is 2 meters. On which nodal line is n located? So is it 1, first, second, third, fourth nodal line, right? Now the first one is when n is 1. So what our goal is in this question is, what is n? Okay, now right away I notice they tell me the wavelength. So I'm going to write this data here. We know the wavelength is 2 meters. Okay. And so what I'm going to do is I'm going to go like this. I'm going to write that the path difference has to equal n minus 1/2 times lambda, right? Now the path difference is the difference between, it's ns1 minus ns2, right? In other words, it's the difference in the line segment here. So in other words, waves traveling from source 2 follow this path to get there. Waves traveling from source 1 follow this path, okay, to get to point n. And there's a difference in the length of those paths, right? And we can see here that the difference is, no problem, 7, okay, wavelengths. Or sorry, 7 meters, right? the difference here, let me write out the step for you. It's 12 minus 5 wavelengths, which is equal to 7 wavelengths. Okay? Oh, pardon me. What am I doing? I'm sorry, guys. I did this wrong. On this side of the equation here, I'm not going to restart my video because it's 15 minutes long. I don't know what I was thinking. I wrote the right equation, but I meant to put the path difference on this side. So excuse my brain fart. Okay, it's I'm better in the morning than I am in the afternoon. So that's my excuse. All right, so look, let's get this right. NS1 minus NS2. That is the path difference. Pardon me. And that's equal to n minus 1/2. I got this right now. N minus 1/2 times the wavelength, and the wavelength is 2 meters. So we're going to put in the number 2. Now here, this is 12 minus 5 equals n minus 1/2 times 2. Okay, so 12 minus 5 is 7. And then I'll write n minus 1/2 times 2. Okay, now I'm going to divide both sides by 2 and solve it for n. So I get 3.5, that goes away, equals n minus 1/2. Bring the 1/2 to the other side by adding a half. So 3.5 plus a half is 4. So n, small n, is 4. So it is on the 4th nodal line. And you see, that's how you do questions like this. All right, I want to leave you with this one. This was one from the, I think, the review exercise in the homework. Okay, so surprise, surprise, radio stations use light waves, and those are, they use radio waves, which are light waves, okay? So, in fact, they're extremely low frequency and long wavelengths, okay, for radio waves. So it says, relatively speaking. So it says here, 2 towers of a radio station are 400 meters apart along an east-west line. So I'm going to draw a little diagram here. Here's my 2 sources, S1, S2, and these 2 towers are 400 meters apart. Okay. Now it says they're radiating phase, that's normal, at a frequency of 1 megahertz. So we know that F, and that doesn't come up in the equations, right? But I'll explain, is 1 times 10 to the 6 hertz. Okay. And it says the radio waves travel at a speed of light, of course, 3.0 times 10 to the 8 meters per second. Okay, in which 2 directions would you find if you were standing at the midpoint between towers? So if you're standing right, I'll use a black line, standing right here, that's where you're standing. Okay, it says what 2 directions would you face, okay, that you would find the intensity a minimum. Okay, so what we're looking for are 2 nodal lines. So what they're saying is, okay, so let's use red. So let's say one of our nodes goes like this, and one of our nodes goes like that. So let's use the first one. They don't tell us which one. There's actually more than one answer, but let's keep our lives easy. What they're saying is, what's theta 1? Okay. And then you could face that way towards the east or towards the west. Okay, now these 2 angles are going to be the same number. It's just one of them is going to be west of north. This is north up here. Okay, and so what we're going to do is we're going to use this equation that the sine of theta n equals n minus 1/2 times, whoops, pardon me, I'm just going to write that better, n minus 1/2 times lambda over d. Okay, so we're going to use that equation. Now, we've got d. We know d is 400 meters. That's the separation of the 2 sources. Okay, n, we're going to make it up what n is. I'm going to say n is 1. Now, what we need to find sine theta is we need the wavelength. So to get the wavelength of the waves, this is where these 2 values come in. So I'm going to use the universal wave equation. Wavelength would equal v over f. Okay, so that's equal to 3 times 10 to the 8 divided by 1 times 10 to the 6, which is equal to 300 meters. Okay, I think I did that right. Yeah, I did that right. It's 300 meters. All right, so now we're all good. We got everything we need. So therefore, the sine theta 1 equals 1/2. I'm substituting in n is equal to 1, so 1 minus a half is a half, okay? And then times lambda, which is 300, divided by 400, like that. So I get 1 divided by 2 times 300 divided by 400, and then I'll take the inverse sine of my answer. I get 22 degrees. So I get theta 1 equals 22 degrees. And then I could go east of north. I could go theta 2 equals 22 degrees west of north. Now that works for two directions. So I can point either east or west of north along that first nodal line. Now if I really wanted another nodal line, I could just set n is equal to 2. What about n equals 2? Okay, well, I could just go sine of theta 2 equals 2 minus a half is 1.5, okay, times 300 over 400. Now, I may get to a point where I get an error, and that means there is no second nodal line. So if I go 1.5 times 300, yeah, so here, if I go like this, I get 1.125, and then theta 2 equals undefined. I cannot take the inverse sine of that, try it on a calculator, just say error. That means there's only one nodal line, okay, in this configuration here. But anyway, I answered the question. These are my two answers. Okay, and that's how you do a question like that. Okay, now there is a piece of extraneous information in here. I'm going to highlight it for you. They say the listeners are 20 kilometers north. That's actually irrelevant. Okay, so this is not relevant to the question. Sometimes you have more information than you need. Okay, I know you think it's mean and tricky. It is. And yeah, I love it. So anyway, there you go. Okay, so there you go, guys. There's some couple of practice problems for you. I think some of those are in the homework. I am sure you will have other questions for me, so please do the homework and ask your questions. This unit can be very straightforward, but like it's all new stuff, so you have to really look at it, okay, and pay attention to the details. All right, so that's it for now, and have a good one, guys.